going to be total how much? 60 Hz. So this one 60 Hz, this one 60 Hz. Like there are two fields like this. They are rotating all the time together, right? So this is, they call it synchronous speed. Shadow speed, they call it synchronous speed. So now we define this. We said Nm, let's say we call it Nr is equal to Ns minus Ns. Nm is what? Nm is the mechanical speed of the rotor. What speed I'm rotating is 50 Hz or 50 RPM, right? I don't know, 50 Hz, we can convert it to RPM to see how many RPM it is, right? So this is the rotor speed. This is the mechanical speed, right? Ns is the synchronous speed of the machine, which here we supply the stator with the frequency of Fs. I'll calculate the Ns a little later. What we can put this, let's put the cap on that. Ns is a synchronous speed. So synchronous speed basically is the speed of the magnet of the stator. The magnet of the stator is rotating with the synchronous speed. The 60 Hz, I put it here. I will convert 60 Hz to RPM. That number we call it Ns. This one is rotating with Ns, the field created by the stator. The rotor, we are rotating it by how much? Nm, right? So Nr is going to be the, I don't know what I call it, this is what we are going to have in the rotor's winding, right? Sometimes do I have a name for it here? Let me see. No, I don't have a name. Let's call it the frequency of rotor 1. It's not frequency converted to RPM. You know what I'm saying? Frequency converted, this one cannot be hertz, those one will be RPM. All of them, they should be RPM. But equivalent RPM of whatever is the frequency in the rotor, right? Now, basically I can write it this way. I can say Fr, now this is really frequency. Frequency of the rotor winding. We have a current in the rotor winding. Frequency of that current is going to be Fs minus Fm. And how to calculate Fs and Fr, Fm and Fs? Let me go over that one first. Or you can say omega r, again another thing, is equal to omega s minus omega m. You can put it any type of equation you want. Ns let's call it Fs. 120 Fs over pi. How do they get that? Is RPM, right? So this one is going to be most probably, this one is what? 2 times 60, right? Right? So basically 2 Fs over pi. I have 2 times 60, right? Yes, this is yes, that will be 4. I said 5, sorry, I said 5. It's 4, it's number of 4. Sorry, I said 5. It's 4, number of 4, P. Basically 60 is coming from 60 is coming from the RPM. You want it per minute, right? Every minute is a 60 seconds, right? 2 Fs over P is the RPS. We'll check out. RPS times 60 is going to be RPM, right? This one is RPM. Keep in mind. The unit for this one is the RPM. They call this one synchronous speed. I put it here already. I put it here. They call this one synchronous speed. They call this one synchronous speed. And we have a synchronous machine. You know, when we get there, I'll explain now what is the synchronous machine. It's coming exactly from here. If you look at here, the rotor, here, look at here. I said the rotor is rotating with Nm, right? It's not Ns. they call it induction machine or asynchronous machine. You know, asynchronous means they are not synchronous, right? This one is NS, this one is NM. The speed of rotor is different from the speed of generator, right? But synchronous machine, which is the last topic of this course, this one is going to rotate with the speed of generator. Now, we know the mechanical speed of the motor, we know the synchronous speed of the stator field, and we know the frequency of the current or voltage induced in the rotor. We are going to define another parameter. We call it a sleep. We call it a sleep. S. A sleep. We call it S. Yeah, sleep is kind of, I'm not sure what how to explain. My English is not that you should explain it. You know, huh?
Like a slip, like a sheet of paper?
No. So, if the sleep is 0, these two they are going to move together. When there is a sleep, a little bit of a sleep, this one they are moving both, but this one is a little bit sliding here, right? A little bit of it, that's the sleep. They call it the sleep. You know, there is a little bit of sleep. I don't know exactly how to say it in English. That's the sleep. Not the one we sleep at home. Now, sleep they define it as NS minus NM over NS. Or it's going to be 1 minus NM over NS. Or you can say 1 minus omega M over omega S. Or you can say 1 minus Fm over Fs. But these two are more common equations. Now let's find out what's the frequency in the rotor winding. What kind of frequency we're going to see here. I have Fs here, this motor is rotating to omega M or Nm or Fm. Let's see what's the frequency here. Let's come back here. We said frequency in the rotor winding, Fr, is Fs minus Fm, right? Let's time this one by Fs divided by F, or factor Fs, let's say Fs, right? It's going to be 1 minus Fm over Fs, right? What is that? That is the slip is usually very small number, like 2%, 3%. We're going to get there, but 1%, worst case 5%. Let's say this is 60 hertz, right? Let's say the stator winding, we plugged it into the three-phase system here. How much is it? 60 hertz, right? And if machine is 1% slip, how much is the frequency of the rotor? Almost 0.6 hertz, right? 60 times 0.41 is going to be 6.6 hertz. Now, I'm going to ask you a question. We said in the core loss depends on the two parameters, right? There are two parts. Eddy current loss and hysteresis loss. In the DC machine, I said the core loss is where? It was in the stator or in the rotor? Good. Why not in the stator? Because the excitation was a DC excitation, right? The frequency was 0 in the stator. So the core loss was in the rotor. Now you tell me where is the core loss in the induction machine and why? Where is the core loss in the induction machine? Again, I have a winding, I have a iron here, right? It's going to be core loss, right? It's going to be magnetic loss. Where is that? Maybe it's in both sides. Maybe in the rotor and the stator. Or in none of them, I don't know. What do you think? Is it rotor? Anybody else? This is stator. Anybody else? Both. So you say rotor. Why rotor?
Because that's AC current.
We say in the stator. Why?
Because the windings are in the state.
We have winding in both. Here also we have one. You know, here we have also one. There is three-phase winding also here. I didn't write, but there is winding also in the rotor. So none of you are correct. No, I'm saying none of you because you say both. You say the stator, you say the rotor. I'm saying no, none of you. So actually, he was correct, but he changed his mind. He changed his mind. The loss is in the stator. This one is clear. Why? The stator has a frequency, right? And it's an iron. So that one we don't have to discuss about. So there is an iron loss in the stator. Why there is no iron loss here? That's the why there is no iron loss here. Hmm? No, the same.
Because the magnetic field is pushing it continuously, so it's not pushing. No.
The magnetic loss depends on what part here? Frequency, right? Frequency. I give you an example. I say this is 60. There's how much frequency here? It's 0.6, right? It's almost zero. It's not perfectly zero, but for example, 98% of the loss is in the stator. 2%, in this case, 99% of the loss is going to be in the stator. 1% is going to be in rotor. Because rotor is almost DC, almost, is not, 0.6 hertz is not perfectly DC, but it's almost DC, right? So opposite to the DC machine, we say the magnetic loss is in the rotor, right? And the stator is loss free, right? Here, the magnetic loss or core loss is going to be in the stator. Because almost, I said, the frequency of the rotor current is almost zero, is SFS. And S is a number from 5% usually to 1% or something like that, very small number, right? So FR is almost zero. FR is almost zero, so there is no core loss in the rotor, right? So that's to clarify the point. Core loss in the state, not in the rotor. Now, okay, let's go to a simple example. I'm not going to go to the equivalent circuit of this machine because that one is a pretty long discussion, and I don't want to go to that one. I'll start with these examples, and I'll leave it when I'm coming back. That one is going to be a pretty long discussion. Let's go through one simple example, to get a little bit more familiar with this part. Instead, we have a induction machine. See, every machine, right? If you have a chance, please go look at it. Every machine there is a plate on it. They fix it here. They put some numbers here. They write some numbers here. For example, rated voltage, rated current, rated power. If it's an AC machine, rated frequency. I don't know, power factor. These are all rated. I'm saying rated, I mean the nominal value. They can work with the different values, but this is a rated value. For example, I am 44, 88 kilogram, I don't know, whatever, the 5'8" tall. This is my rated value, If I change my shoes, maybe I'm a little bit, taller or shorter. If I go eat more, maybe my weight changes, But the rated value, they are what? They call it nominal values. These are the kind of fixed numbers. These numbers, they call it rated. You can look at every machine and find out this one, and you can get a kind of imagination of this machine. Where's the 85, I think 83, 84, something like that. 83, 5'8". You have a kind of imagination of this guy, how tall he is, how big he is, and those kind of things. This one is going to give you the same imagination. This is 5 kilowatt motor. Can it work with 1 kilowatt? Yeah, it can. Can we work with 10 kilowatt? No. Not more than that, right? Not more than that. 10 kilowatt is very good, right? So, for example, I can carry on based on what I said. I can carry on, for example, 20 kilogram of the load, right? Can I carry on 10 kilogram? Yes. If I can carry on 20 kilogram, definitely I can carry on 10 kilogram, right? But can I carry on 50 kilogram? No, right? So my point is this the rated value? It says where this machine is, how we can handle this machine. Less than this one, okay. More than this one for limited time, very short time, maybe 5%, 10%, not more. Usually they design the machine to work a little bit more than their nominal value. 10% is kind of a lot, the machine is going to get really hot if you run it long. But the rated value, you can run it forever. You can run it forever. It's going to get hot, but it's not going to be dangerous. The temperature is going to reach to a steady state value, which is not dangerous for the machine. But if you run it 10% overload, this one is going to get hot, and it's not going to get to a steady state number. Maybe after 10 minutes, it's going to get really hot. It's not going to burn right away, but if you run it for 2 hours, it's going to burn. Right? If you open the refrigerator door and let it board, what's going to happen? You have a refrigerator at home, all of it. If you want to kill it, what you can do? Just open the door, right? Leave it there in summertime. What's going to happen? It's going to run. Because right now what it does, it's designed like this. It's going to, for example, run, I don't know, 1 hour. It's going to be cool enough. It's going to be off 10 minutes, or something like that. You can see the well turn off, right? So basically, it's going to cool down, and it's going to be okay. Again, after the temperature somehow a little bit changes, it's going to run again to cool it down, right? But if you keep the door open, never ever it's going to be cool, right? It has to run until it dies. It's going to be hot and get hot and fast, right? So I said all this story because when you read all this problem, they said we have an induction machine, 208 volt, 60 hertz, 4 poles, with a speed of 1755 RPM. So we have a machine. The rated voltage of this machine is 208. What does it mean? 208 60 hertz. What does it mean? We can connect this system to a 3-phase. For induction machine, we don't say 3-phase. By default, it's there. We have a single-phase induction machine, but usually they mention that. If it's a single-phase, they say single-phase induction machine. If they don't mention, by default, it's a 3-phase machine. So basically, this machine, we can handle it to a 3-phase, 208 60 hertz. It has 4 poles, and the rated, the speed of the machine is 1755 RPM. What does it mean? When you put the rated load, I don't know, 10 kilo, whatever it is, it didn't tell us how much it is. But when you put the rated load of the machine, you plug this one to the 208 60 hertz, right? And you put the nominal load in this machine is going to rotate to 1755. That will be the speed of the machine. Now I said calculate this kind of thing. Calculate the synchronous speed. How much is ns? Calculate the slip. How do you pronounce it? Slip. S, and calculate the FR. Frequency of the current in the rotor winding. Frequency of the current in the rotor winding. So how much is ns? How much is ns? 120 F. Usually we don't put S anymore. When we say F is the frequency of the stop line, well, you can put FS also. Because this one is going to connect to the stator of the machine, right? Over P. So it's going to be 120 times 60 over what? 4. So this is the 30 times the 1800 RPM. Look at here. This is the nominal speed. This is synchronous speed. Usually, this is another thing to keep in mind. Usually the speed of the rotor in the induction machine is very close to the synchronous speed. How much is the S? 1 minus Nm over Ns, right? 1 minus 755 over 1800. So it's going to be 2.5% times percent. It's going to be 2.5%. How much is the frequency of the rotor winding, the current in the rotor winding? SF, right? How much is F? 2.5% times 60 hertz, right? So this one is going to be about 1.5 hertz.